Hey guys, Mr. Marone here. We are coming to you with G.co.C.10 notes, day one, where we talk about all the different things involving triangles and all the different relationships that we have that we can look at in regards to our different triangle theorems. So the first one we're going to start with is the idea that the interior angles of a triangle add up to 180 degrees. And for each of these proofs, there's three different types. There's an informal proof, there's a classic proof, and then there's a transformational proof. So we use our transformation technique that we've learned already. The informal proof, I'm going to allow you guys to try on your own. So you're going to cut out a triangle, rip each of the corners of the triangle off, and lay them together and see what happens so that they're sharing the same vertex. And what should happen is it should form a straight angle. Okay, when you put all three of those together, it should look something like this, where there's your shredded ends of your pieces, angle 1, 2, and 3, and you end up with a straight angle. I want to do a more formal proof of this. Okay, so what we're going to do to be able to prove this is I'm going to put in a line BD parallel to the base of my triangle AC. Okay, so the first thing we've got there, our first statement, is that we have AC parallel to BD. Then if we look closely up here, we have that angle 4 plus angle 2 plus angle 5 equals 180 degrees. And our reason for that is we have a straight angle. And straight angles equal 180 degrees. Okay. Now, if I take that out and we think about our parallel lines that we talked about in G.co.C.9, we know that 1 and 4 are alternate interior angles. So I've got alternate interior angles with 5 and with 3 here. So step 4 is that angle 3 is congruent to angle 5 by alternate interior angles. Okay. Once I have these, we can use substitution, replace 4 with 1. So I've got angle 1 plus angle 2, and then I'm going to replace 5 with angle 3. That equals 180 degrees, and the reason why I can do that is a substitution. And I really did a double substitution, so we'll say it's 2 times. And now I've shown that angle 1 plus angle 2 plus angle 3 equals 180 degrees here. Now, if we wanted to see it one other way, we could do a transformational proof. Now remember, we can use our techniques of transformation, whether they be translation, rotations, reflections, dilations, any of those things that we've talked about to perform one of these proofs. What I'm going to do today is I'm going to translate triangle ABC, and I'm going to move it along the ray or the vector AB. So I'm going to start at A and move it up to point B. And that's going to give me this second triangle that looks just like our first triangle. And I end up with C prime here. I have B prime here, and B is also going to be known as A prime. We have an isometric transformation. Since translations are isometric, all our angles are preserved. Okay. Beyond the angles being preserved, we also know that I've got parallel lines here. So in particular, I know that AC is parallel to A prime, C prime. Or if you want to call it point B, we can call it BC prime as well. Okay. Knowing that we've got the parallel lines helps, but also having these angles being preserved helps. So if I wanted to reference B prime BC as an angle, this angle down here, it's going to be congruent to angle BAC right there. Those are going to be congruent because we've got corresponding angles given those parallel lines. So we can put a number 1 here. Now, we also know with alternate interior angles, if I've got those two parallel lines and BC as my transversal, that angle 3 and this spot here are going to be congruent. So we can say that angle C, angle 3, is congruent to angle C prime BC. That allows me to place a 3 up there, and it allows me to say that at vertex B, angle 1 plus angle 2 plus angle 3 equals 180 degrees. We've got a straight angle right here at vertex B by using parallel lines along with angles being preserved due to an isometric transformation. So all that stuff we focused on earlier in the year is now all coming back as we tie in here with our triangle proofs. Now that we've seen a couple different ways, we know that the inside of every triangle equals 180 degrees. I'm going to give you guys a couple seconds, and when we come back from the pause, all 4 of these will be filled in, knowing that we have 180 degrees as the inside measure of every triangle. Welcome back. So as you can tell, I used the same process for each one of them with the exception of letter D, where I added the 2 angles they gave us and subtracted from 180 to get my final angle. I had 40 for letter A, 59 for letter B, 58 for letter C. Letter D, they told me that angles A and B were the same, so I made each of them x, and I added all 3. 50 plus the 2x equals 180, and solved for x there, and I got that angle A and angle B would both be 65 degrees. That's everything we have in regards to triangle sum. The next one we're going to look at are isosceles triangles, or triangles with 2 sides having the same measure, and trying to show that the 2 base angles, the 2 angles that are created by the base and the shared sides, that those are going to be equal. Okay? The paper folding one, I'm going to allow you guys to try on your own, but you should see that the 2 angles fit right onto each other when you fold over it. Okay? We're going to look at more of a classic proof here. So they gave us a little bit of information. They told us that triangle ABC was isosceles, and they told us that BD was the perpendicular bisector of angle B. Having a perpendicular bisector tells me 2 different things. We're going to address the perpendicular line and the bisector separately. First thing we're going to say is that having perpendicular lines tells me that angle ADB and angle CDB equal 90 degrees. And the reason is that's the definition of a perpendicular line. Okay, and we could even add one more step and say that angle ADB is equal to angle CDB, because all right angles are congruent. They're all 90 degrees, so they're all going to be congruent to each other. Okay, so now I've got congruent angles there. We also know that AD is congruent to DC because of this idea of a bisector. We know that that's the definition of a bisector, that AD and DC are going to be congruent to each other. We need one more piece of information, and we have it right here, that BD is congruent to BD because it is reflexive. Every side is congruent to itself. So I now have 2 sets of sides with an included angle, so we can say that triangle ADB is the same thing as triangle CDB, and that is by side angle side. And our last thing is we were aiming to prove that angle A was congruent to angle C, and we can say that's congruent by CPCTC. So it's a bit of a longer proof. It's an 8-step triangle proof, but at the end of it all, we showed that angles A and C were in fact congruent to each other, the base angles of an isosceles triangle. Now, if we wanted to use a transformational proof, what we're going to do is we're going to use a reflection. So we're going to reflect over the perpendicular bisector. Okay? When I do that, I have that A maps onto C. A goes right over and lays on C if I were to reflect over segment BD there. Okay? We also know that B maps onto B, it maps onto itself, and we know that D maps onto D. Since reflections are isometric, we know just from our previous proof as well, when we did transformations, that angles are preserved. Okay? That's crucial. Since they are preserved, angle A is still congruent to angle C, and since they map onto one another, they're the same thing, and it allows us to say that A is congruent to C, or if you would like the more specific angle, angle BAD is congruent to angle BCD. So it's a quick transformational proof there for us. Okay? And a more formal version of our folding proof from the informal one at the beginning is if I use symmetry, isosceles triangles, that they have one line of symmetry. And that was from G.co.A.3 all the way back. So since these triangles have a line of symmetry, that means that half of triangle ABC maps onto itself. In other words, we can fold it right over the top, and that tells us we are mapping angle A onto angle C, making angle A congruent to angle C. All of this leads us to be able to solve these types of problems, these now you try some problems. So I'm going to pause the video and let you try to solve for these missing angle measures, now knowing that the base angles of every isosceles triangle are congruent. Welcome back. So as you can see, for the first one, I subtracted the base or the vertex angle by 180, got 82, and cut it in half to get my two base angles, each at 41. In B, we had to reverse the process and double 78 to get both base angles, and then subtract that from 180 to get 24 as our vertex angle. In C, they gave us a base angle and they wanted the other base angle, so that was a quick and easy one. And in letter D, we had to do probably the longest process you'll do with one of these. We took the vertex angle and subtracted from 180, got the total of the base angles and cut it in half and got 72 as our base angle. I then had to find angle ACD, which was 180 minus my interior angle, 72, to get that 108. Then I had to subtract 108 from 180 to get the two base angles, A and D, in our right-hand triangle, and then cut that in half and got 36 for my total. Now that you have seen all of these notes on day one here, you're going to try pages 5 and 6 in tonight's homework, in your homework packet. See if you can get them, see what happens, and bring in any questions you may have in class tomorrow. Have a great night.